It's a great pleasure to be here with you this morning, and what I'm going to try to do in the next 50 minutes or so is to tell you a story about how we find planets around other stars and what their natures are, what we've learned about them in the last 20 plus years, and then focus more in the middle of the talk on how planets form and what that can tell us about what their compositions are. And then at the end, my whole goal is to tie this all back to the theme of the possibilities for life in the universe, which I think was the theme of this semester's series. So hopefully I can do that in a timely manner as we go. All right, so I like to start off by explaining why this should be connected to the emergence of life in the universe. And my take on that is the following, that there are astronomical limits to the emergence of life in the universe. And first of all, life requires energy. It requires energy to metabolize and to grow and also to reproduce. And being near stars in the universe is a good way to extract energy from your environment. So being near a star is probably not a bad idea if you want to be alive. The second part is that many people, not all, but I would say the vast majority of scientists working in this area think that life is a planetary phenomenon. And by that I mean the biochemical origins of life, which is a huge and fascinating and complicated problem we haven't made a lot of progress on and needs a lot more work, is easier if you can bring the necessary ingredients together on a solid surface. And a solid surface, particularly planetary surfaces where there are boundaries and disequilibria, are a place where you could possibly assemble those things. So we want to know what the compositions of forming planets are, whether they have those necessary ingredients, and how common certain kinds of surfaces are around stars in our Milky Way galaxy and actually integrated over the whole of the cosmic time. And the reason why I care a lot about the latter part of that statement, about integrating over all of cosmic time and what might be the life in other galaxies, etc., that's because I just want to know over our whole universe what the prospects for life are. And because I want to know that, I need to understand formation. Because I can look locally at many systems that are very close to the sun, but the vast majority of the systems will be inaccessible to me in any way for many, many, many lifetimes or forever beyond the Hubble sphere. So we need to understand formation so that we can extrapolate, and how that formation depends on initial conditions. Okay, so many of you who follow this topic will have heard the term habitable zone. I hate that term, habitable zone. It should be, I don't know, the watery, liquidy zone or some other term which tells you about the temperature that liquid water could exist on the surface of a solid body. And that's what it's really meant to refer to in a diagram like this. I hope you and the others in the next room can see this arrow, which I'm now moving on the slide. If you look at our solar system with the luminosity of our star, then you can calculate a place where water could exist as a liquid, so there's a range of temperatures where we know that to be the case. And as you change the luminosity of the star, if you go lower, then that zone moves inward, closer to the star. And if the star is much brighter, then that zone moves outward. So that gives you some idea. Now, don't get me wrong. I think that following water is a good way to understand and look for the emergence of life. But I think it's a little arrogant, maybe, to think that we completely understand all of the systems and all of the places in all of the systems where there could be liquid water and where life might emerge. So while this band of blue is not a bad place to look for life, I would myself not ignore all of the other zones in planetary systems. Okay, so now I want you to have a quick look at this beautiful piece of machinery here called the ORI, which is a lovely mechanical device which is meant to reproduce Kepler's laws and to tell us what the orbital period of each of these planets are as a function of their distance from the central body. And I hope already you can see, and those in the next room if the camera's on me appropriately, you can see the inner planets are moving more quickly, and as you go out, the planets are moving more slowly. And if you're an eagle eye, you can even look at these outermost ones, and hopefully by the end of the lecture, you might have noticed from your parallax perspective that they might have moved a little bit against the background of whatever you're looking at it against. So this is our clockwork universe in our solar system, and these are our lovely planets that we focus so much on. I'll refer back to this in just a few minutes. Now, here's the audience participation part of the talk. I ask you this question. Do you think that planetary systems like our own are common or rare in the Milky Way galaxy? So I've restricted it to the Milky Way, and I'm only giving you two choices, common or rare. There are many other possible answers here, but it's a binary vote. You have to make a choice, even if you don't like the choices that you're being offered, right? So let's do the vote. I can't see the hands in the other room, but I ask them to vote as well. How many think that planetary systems are common? Raise this hand. And how many people think that they're rare? Raise this hand. Well, common won by a large, large margin. So we'll come back to that in a minute. I ask this question in every context I can, and it's particularly fun to ask the PhD students who are studying in this research area this question, and they all have strong opinions about their answers, as I'm sure you do too. But to me, the devil is in the details, as it often is. And when I say like, to paraphrase Bill Clinton, what do you mean by like? Our system has many attributes, and depending on which ones you think are important, you might give those more or less weight in saying whether these systems are common. And as Fred taught me probably 25 years ago, everything in science is a probability distribution function, and if I ask for any specific value that has one unique answer with infinite significant digits, the probability of reproducing that is 0. I have to integrate over a range of values that I think are interesting. And if I'm looking at many different properties, I have to integrate over a range in each of those properties, and then I need to multiply these probabilities together. So if I start by saying that we need an Earth-like planet, okay, well I can assess how common those are in terms of Earth size and what orbital radius they are. Okay, so maybe that's one probability function I can assess and come up with a number. Then maybe I say I need Jupiter, and it has to be between 4 AU and 6.2 AU. Okay, I can measure those and integrate over them. The more specific I get, the harder it's going to be for me to come up with a system exactly like our own. So there is no system that is exactly like our own, but some are more or less like the one that we have. Now, when we look at these planets shown up here on the screen, there are vastly different kinds of planets here. There are these tiny ones that are very small and low mass, but they have very high densities. They're little rocky guys. There are these two big gas giant planets, which are very large in mass and radius and very low density, predominantly gaseous material, not unlike the sun. And then there are these two ice giants, which are different still again, that they have almost equal proportions of gas and dust or solid materials within them. So already we have quite a diversity, but even there, that's not even scratching the surface of it yet, compared to the planets that we found around many other systems. Each of these has a very different mass to radius ratio, which determines the bulk density, and that gives us a real clue about what the planets are made of. In our system, of course, we can even go there, and if we're lucky, scoop up bits of it, and if we're super lucky, we could bring it back. That's very expensive, but we can do that. In other systems, we have to rely on remote sensing, or looking from afar at the properties of these planets. So now I want to talk for a few minutes about how we detect planets. The first method shown at the top is the famous called radial velocity technique. It's the Doppler technique, and if you've ever heard a siren go by you on the street, you kind of have a feeling for what this is. As the signal is moving closer to you, the frequency increases, and then as it moves away, the frequency decreases. And of course, you've all been subject to Doppler radar on your weather channel, but also from policemen and women stopping you for speeding. So we can measure the speed of things using this technique, and it was very effective at discovering many hundreds of planets. Another technique is the transit technique, shown on the lower left, where a planet moves in front of the star and diminishes the light from the star as it's in front and then moves out, and then the light comes back up. That's what's shown by this white curve here, showing you the brightness of the star over time. It dims a little bit as the planet is occulting the star or blocking the light from the star, and then it comes up again. This technique has been responsible for finding the most planets, and that's mostly because of the amazing Kepler satellite. Now, to show you the amazing power of the Kepler satellite, I'm going to try to show you a video here from YouTube, so you can all go home and find it. It's called the Kepler ORI number 4. There it is. Now, what you're seeing here is all of these Kepler systems that have been found from this transit technique. The colors are related to the temperature, where blue is cold and red is hot, which is weird for me as a physicist. And the size is proportional to the radius of the planet. We don't know all the masses of these things, but we can measure their radii rather well. And you see that solar system in the middle there? Now you can't see the little dots going around it so slowly. Well, that's this one. Okay, this is the 3D version. That one's in the middle, but look at all those little ones traveling around so fast. That's because the Kepler satellite, this transit technique, works best when the planets are close to the star. So if you imagine tipping a system where you were looking at the pole, you wouldn't see any signal in the dipping of the light. When it's edge on, you do see the signal. And the closer the planet is to the star, the easier it is to get that geometry where you can see it. So, I don't want you to look at all kinds of weird YouTube videos, so let's stop that right now. That's my daughter's here. She's probably responsible for that Peppa Pig scenario. So let me get my cursor back and go back to presentation mode. That should fix it. There we go. Whew. All right. So we have transits and radial velocities, which are very good at finding planets close to their star. Now, the one that I focus on is called direct imaging. I want pictures. I'm a very visual person, and I would like to see pictures of planets. This is a picture of a planet. I mean, it's not that impressive of a picture, but there's a really bright star called Beta Pictoris, the second brightest star in the Pictoris constellation, and there is a little planet by it. It's a very massive planet, several times the mass of our Jupiter, about 8 times is our best guess. And it's about 6 to 10 astronomical units, or the mean distance between the Earth and the Sun, this distance here. It's that much farther out in the system. But it's a young system, and that's important because the planets, when they're young, are very bright because of their energy of their formation, and they're much easier to see when they're young. So this is a super young system, about 12 million years old, and we have a picture of that planet. Very excited about that. But it was brutally difficult. And to illustrate that, I would like to show you a couple of quick demonstrations. The first demonstration is designed to show you how hard it is to resolve objects, even with the largest telescopes, from the ground. So now what are we seeing here? Sorry? I have to turn on the light. Now I've forgotten where I need to turn that light on. Oh, there was a little black. Oh, here it is, right. Right, there are the lights. So hopefully what you're seeing through our telescope is two, you're not going to see my hand unless I block the light, but you see two little lights there. And now I'm going to turn on the Earth's atmosphere in this little system, which is going to send bubbling hot air from this toaster in front of the telescope, and it's going to blur the light. Oh, I'm going to cut in front of it again, so that's not good. It's going to take a minute or so to heat up. And then we'll see the lights flickering there. There we go. Well, this isn't such a bad atmospheric night. You can actually resolve the two stars and separate them pretty well. Oh, now the heat is really cooking up here. Now it's getting very, very difficult. This looks more like what I see in a telescope. It's very difficult to resolve two objects of equal brightness if they get too close together. And the limit for that is set by the wavelength of light that we're looking at and the diameter of the telescope, inversely proportional to the diameter. So the bigger the telescope, the easier it is to resolve two objects that are so finely close together like this one here. But just like the toaster is generating hot air that's moving in front of our telescope, the turbulence in our Earth's atmosphere blurs the images that we see. Great. Now, the way we correct for that is to use a technique called adaptive optics. And that is being illustrated in this kind of awkward animated GIF image here. So I'll wait till it starts over again. You have a wavefront that comes through and hits your camera and makes a very blurry image of a telescope. We then send signals back to correct the wavefront in the telescope, and instantly the image in the lower right. Let me illustrate again with my cursor here. So now we're correcting, the straight wavefront comes through, and we get a perfect point source down here on our camera. One more time, funny wavefront, blurry image. We measure that signal, we fix it, and we get a very nice sharp image here. And the way we measure that is through this thing called the wavefront sensor, which then does a calculation of flattening what it should be and then we send the signals back to correct for it and get the beautiful images here. I'll let that run because it's a little confusing. The other problem that we have, in addition to resolution, is contrast. Planets are very tiny compared to their stars and very faint in the luminosity, even more so. So it's hard to see faint things near bright things. And if I can do this correctly, let me push this button. Is that light working there? Okay. Now it's off. There we go. How many physicists does it take to turn on a light bulb? All right. So you see this nice light. It doesn't look that difficult to see. And you can also maybe see that it's reasonably well separated, our two light sources. There's one here, and I don't know how far back, perhaps in the back row. Can you see in the back row that there's two different sources? There's one light source, and this one hasn't been turned on yet, but can you see that it exists? They're about this far apart. Can you see my two fingers? Yeah. So the resolution isn't a problem, okay? You can see that I have two fingers, and they're well separated. Now I'm going to turn on the other light. Whoa! Sorry about that. You may need sunglasses in the front row. I better turn this off pretty quick. It's really hard, if not impossible, to see the fainter light. This is a contrast problem, to see a bright thing next to a faint thing. Some of you were holding up your fingers to block out the light, right? That's what we do. Well, we don't use our fingers, but we use very fancy optics called coronagraphs. Unspeakable things are done to the wavefronts in the pupil of these optical systems. And there are various ways you can suppress the light from the central star because the beam of the central star is on the optical axis. And you try to relax the blocking when things are outside of the central zone. And this is just a demonstration. You'll have to trust me that folks have done this right. Without a device, this is what a very, very fine resolution image would look like at the diffraction limit of our telescope, the most perfect we can do. And then when I turn on or put in a device called a coronagraph, which is a way of blocking out light from on the optical axis, I can see fainter things that are near it. And that may not be impressive. You might ask me what is the scale of these two images, etc., because you can manipulate images. But here is now a plot of brightness along the up and down axis versus angular scale or radius on the x-axis. And this black line that I'm tracing over with my arrow is what the profile of the light is without the device, and the blue one is the profile with the device. Basically, we can drop out the starlight by a factor of 100 to 1,000. And this helps an awful lot in our ability to see faint light next to very bright lights. Put that off. Okay. So there are two examples, and I think I'm supposed to turn this off too. Did I get that right, Monica? Yeah, look. Woo, I remembered. I can follow instructions. All right, so we want to take pictures of planets, and this is perhaps our best success. I wasn't involved in these, although I've done follow-up observations of these planets. I didn't discover them. Christian Marois, a good friend of mine, and others did about 8-9 years ago now. This is a 4-planet system. These planets are very far away from their star, tens of AU, so sort of way out here in this range in our little model solar system, and all the way out here, way beyond the planets that we have in our solar system. And all 4 of these planets are big, beefy planets. They'd never skipped lunch or dessert. They're many times the mass of our Jupiter. So that's a weird system compared to the one that we live in. And the arrows you're seeing are actually orbital motions that have been observed over a period of many years now. It's just wonderful to see. I didn't emphasize it before, but it's quite amazing. This clockwork mechanism we made, based on the laws of gravity that help us is there something safe I can drop? Anyway, maybe not. I'll drop a pencil. I can do that without breaking anything. Great. I can predict how long it's going to take for that pencil to drop there. I can predict the orbits of these planets. I can predict the orbits of those planets and all those other thousands. I mean, that still gives me goosebumps to think that these laws of physics that we develop here on Earth can apply over such dramatically different scales and environments. It's really lovely. So we always show this picture because it's one of our best successes. But if we are honest, we have to compare to all the other methods which have been much more successful to date. Here is a picture of many of the planets that have been discovered, not absolutely all, but a good census of them in mass. Again, along the up and down axis is planet mass in Jupiter, or Earth masses, excuse me. So here's the Earth, shown in blue at 1. And here's Jupiter at about 300 Earth masses, shown there. And on the left and right axis is the distance from the star to the planets that have been discovered. And the black ones here are the ones in our solar system: Jupiter, Saturn, Uranus, Neptune. These are the ones we found around other stars. So the circles are all the ones from radial velocity. The orange ones are transit, where remember, we only get the radius. So we also had to go back and try to measure their masses, again using the radial velocity technique, because the signal that we see in that Doppler shift is proportional to the mass of the planet. That allows us to get the masses for those objects. And these numbered blue ones are the ones we've had pictures of. There's only about 10 of them, so I'm embarrassed. You know, there's 3,000 Kepler planets and 10 imaged planets using our big telescope. So we need to do better, and we will, and we're doing it now. And the expectation is that this is what will explode in the next decade, as opposed to the last 2 decades, which have been very successful. Now, we want to explain these distributions. It's not a random scatter, but you can also notice that it's hard to see some objects, and we would have seen Jupiter by now. With certain kinds of techniques, we could see things as small as this, but there's a big space that hasn't yet been explored, and in particular, this direct imaging. We need to move it down so that we can detect planets like Uranus and Neptune at large separations. The farther the planet is from its star, the easier it is for us to take pictures. So that's why these blue ones are all way out here. And of course, the best thing for us is to overlap. When we have 3 different techniques that can see the planet all at the same time, this is the best, because we get the most information we possibly can about the planets. Knowing mass and radius gives you the density. That gives you some ideas about the composition. But what we really want to do is measure spectra, look at the fingerprints of the atoms and molecules in the atmospheres of the bodies, and see what they're made of. We want to see the carbon dioxide. We want to see the water vapor. We want to see the molecules that ultimately could give rise to life. We want to see those in the atmospheres. And direct imaging and getting spectra of those resolved objects is a beautiful, beautiful way to do that. All right, I think I've eaten up way too much of my time telling you how we find planets and what the demographics of planets are, but let's spend a few minutes talking about how they form. Well, stars tend to form in groups of hundreds of stars together. That's a very common mode of star formation. This is a picture of such a star cluster. And many of the objects in this picture are about the mass of the sun, but even more are lower mass than the sun. And there's a few higher mass stars thrown in too. The environment can matter a lot because there can be dynamical interactions between stars where planets that could orbit one star could get flung out, for example. There can be violent events like supernovae. Those are extremely rare, but they could happen once in a while. There's also light, bright blue ultraviolet light from the most massive stars, this blue guy you see down here, that can shine and boil away the material from which planets can form around young stars. So the places where stars form matter a lot in the kinds of planetary systems that we will end up with, and it's something that Fred Adams, our host this morning, has worked quite a bit on. Now, I'm not going to go into the vast details of how material evolves around young stars. There's a whole talk about that, and you've heard some of it, I hope, from earlier talks like Dr. Ryder, who gave a talk, I think, in October. But as the part of the star-forming process, material collects in disks of gas and dust around young stars. And initially, those disks are pretty massive. They have a lot of stuff in them, and you could form many planets from the stuff that's there. The processes that change and evolve those disks are very, very complicated. And over time, this is a time sequence from the upper left to the upper right to the lower left to the lower right. Over time, the disks dissipate through a variety of mechanisms. They throw some of their gas and dust onto the central star, which is still growing in mass. In some cases, planets will form, and that is a way to lock up material in the disks. And one of the most important ways, again, is that energetic light from the central star shines down on that gas and boils away some of the material in those disks. So you have a clock of a few million years in which to form the planets that you're most interested in. And disks and those processes depend on the local conditions and the mass of the star. So there's a lot of complicated stuff that we need to take stock of. Now, there are lots of interactions and physical processes that go on between the little bodies as they grow and the planets that finally form. One of the first things that happens is two dust grains will bump into each other and stick together. And then maybe another, and another, and another, and they'll grow up from tiny little dust bunnies under your bed up into rocks and boulders and the size of this desk and ultimately the Earth and so on. One of the important processes is how solid particles interact with the gas, and I'm referring to this plot on the lower left, which is pressure on the up and down axis, and again, separation from the star on the left and right axis. A gas molecule that is looking towards the star will notice that there are a lot of other gas molecules in its way between it and the star, and in fact, it's feeling some pressure. It's getting pushed by that pressure from the molecules that are inside. And that's kind of nice, you can sort of rest on the pressure. And instead of having to orbit at the Keplerian velocity, which Newton and Kepler would tell you you had to, you can actually rotate a little more slowly and a little more leisurely on a Saturday morning because you've got some extra support, like a pillow, of that gas pressure inside. So that's what a gas molecule can do. A big, beefy rock like myself, my volume to area ratio is different than a gas molecule. And so I am much more interested in orbiting at exactly the right velocity because I don't feel so much that pressure that I described. So I'm going to march around my star like I'm supposed to, but because those gas molecules are moving more slowly, I'm facing a headwind. It's like riding your bicycle. Whenever I ride a bicycle, it's always uphill, right? Either way. So same way, I'm trying to ride my bicycle around the star. I feel this tremendous headwind. I get tired, and I start spiraling into the star. And in fact, that is a major loss mechanism for solids. So we need to find a way to stop that. Now, you may not have understood the details of the process I just described called gas drag, but imagine if you have a gradient in gas, like is shown in this plot, but suppose there's a little local place where there's a bump, even relative to the overall drop-off. What that's going to tend to do through the same process is collect material that came in from the outside, but also collect material from the inside, which will get pushed out. And then all these rocks will get concentrated in one place, in a pressure bump, and that's a great place to form planets. So we are looking for discontinuities or special places in these disks where planets can form. If this can happen efficiently and fast, and you can get up to a big object quick enough, that object also starts growing gas around it. It starts pulling in gas. You can open up gaps in a circumstellar disk. And once you start having rings and gaps in the disk, you create opportunities for pressure gradients near you because you've changed the gas density. And you also start disrupting in big ways with launching spiral density waves and other complicated things, the global structure of the disk. So here's an artist's conception of what that might look like, where many little bodies are forming in this disk and creating new discontinuities at the places where they form. So this could be kind of a once you get started, it can just go and maybe wipe out large regions of the disks in forming planets. Well, that's a nice story. I always kid my theoretics colleagues because they love to tell nice stories, but I like to see observations or at least experimental evidence that can support their nice stories. And lo and behold, we do find them. These are some of the latest images from a ground-based telescope with the adaptive optics around a star with a horribly boring name, HD 142527. Here it is. The star has been blocked out so you can see more clearly, but there's so much rich structure in these disks and so many complex processes going on. This hole that you see here in the disk on the left is twice the radius of our solar system. It's this big. So what is in there? There's probably just chock-a-block full of planets in there. We haven't seen them yet, and we're trying as hard as we can. On the right-hand side, this blobby, weird-looking thing is a millimeter wave image from a new telescope that's come online in the last few years, and we can compare these two wave bands. On the left, you're seeing light scattered from the star off of small dust grains, and on the right, you're actually seeing the emission from the grains themselves at the cold temperatures in the outer disk. And we compare these to build models of these systems. I should say from a Michigan perspective, these are the kinds of images on the left that we can make with our Magellan telescopes in Chile, to which we have preferred access, and it's an amazing research tool for colleagues here at the University of Michigan. And on the right-hand side, we have also access to a millimeter wave telescope in Europe that we as Michiganders can access and make images like this. So we have a fantastic research opportunity because of the strength and facilities our department offers for us. All right, back in to zoom in and wrap up a little bit. These are the same planets I told you before, and now I've put some lines on it just to remind myself to tell you that from the radial velocity data, that Doppler method, we know that there are many fewer planets, there are many more planets as you go down to tinier and tinier masses, and when you go out, there are more planets per logarithmic distance interval as you move away from the star. So these have to be explained by models. And I've just labeled them, I won't go into the details, but the purple one is called GI, gravitational instability. The blue one is called core accretion. It's kind of our standard model, and it's predicting that it's easier to form planets this way out at these radii. There are many aspects to the theory, and there are lots of wiggle rooms, but basically all of the theories fail to explicitly explain the distribution of points that we have, but there are new ideas that are coming, and we're trying to test them both from the statistical point of view, like what is the big picture given all the thousands of planets we found, but also by looking specifically at individual systems. So I couldn't resist showing you these kind of science-y, weird-looking pictures from a recent paper of ours where we think we've spotted a protoplanet just in formation in a very outer zone of a disk around a young star. Again, the star has been blocked out. You're seeing thermal emission, not scattered light, but mid-infrared thermal emission of a protoplanet here. And it's a dot which is sitting on top of a large region of extended hot gas and dust. And we don't exactly know what's going on here, but we believe this to be a body of about 10 to 30 Earth masses that is just for the first time gathering gas and dust around it. We believe it has a disk of material around the protoplanet from which moons could form, just like the Galilean satellites in our own system. Now, I'm telling you now a story which I don't have a lot of data to support, but we're trying to characterize these objects and get spectra of them and to see what molecules are in the protoplanets and try to see if we can detect the circumplanetary disk around it. The reason I mention it is, number one, it's again the kind of work that we plan to do in my group with the 6.5 meter Magellan telescopes in Chile, again, that the University of Michigan is a key partner in. But also because these observations of a planet forming that big, which would eventually become the Jupiter-sized planet, way out here, our theories really fail to explain this kind of system. So we are looking at other models, and if there are any experts in the audience, kind of pebble accretion or streaming instability is a very attractive model for a body like this. Well, I've talked a lot about these big gas and dusty disks and forming protoplanets that will end up like Jupiter here in our own solar system. But we started talking about Earth and rocky things and getting molecules together to initiate biochemical origins of life. How do those things form? Well, it's a similar story on some hands in that you still need to gather rocky, tiny things up together. This is, again, a complicated science-y plot where on the up and down axis you have planet size starting all the way down at tiny dust grains, going up to kilometer-sized bodies, embryos of 1,000 kilometers, and then big planet things you might recognize like an Earth at 10,000 kilometers or more. And this is now time in 10,000 years, so it's in the exponential notation. 10,000 years, 100,000 years, 1,000,000 years, 10 million, and 100 million. We grow up to these bodies, and then there are gaps and fits and starts where we need to leap over events, but then finally, at some point, we have a disk that's mostly cleared, and we have a handful of big objects. And ultimately, over tens of millions of years, those big objects will find each other dynamically and smash into each other in a rather chaotic way. You might have 10 Mars-sized objects. No more gas left in the disk. The giant planets have already formed, and all of the gas has boiled away because of that intense ultraviolet radiation from the star, and you're left with 10 Marses around the zone of Earth. And ultimately, those things need to collide through dynamics, chaotic dynamics, to ultimately form something like the Earth. And you probably have heard the story of how we think our moon formed through such a system. It was probably the last of these oligarchic, chaotic collisions. A small Mars-sized object hit the Earth, proto-Earth, at some angle, and the resulting system was a molten disk of about several Earth radii from which the moon formed. I keep telling my colleagues, we have to look for such a thing, because with my infrared vision telescope, such a hot, energetic event would be very, very easy to see. The problem is that they cool super fast. So they cool in about 10,000 years, which may sound slow, but in terms of the millions of years of timescales that things I look at evolve, it's a blink of an eye. So I would have to be super, super lucky to catch an object in this phase. But if I did, I could learn a whole lot about how Earth-like planets form and the composition of those protoplanets and how watery and how much carbon they might have in them. The other thing I wanted to mention as I'm starting to wrap up here is that the places in this environment where the planets form tells a lot about the composition of the bodies that they would have. We've talked already about how our inner planets in our solar system are rocky and have very high densities, and then there's the gas giants out here, close to the transition point where you might have liquid water turning into ice water in our own solar system, and then the ice giants here. Depending on where things form, they will have a certain composition related to the ability of hot gases to condense. And this is a topic that I am really ignorant on. I barely remember my chemistry, my first 2 semesters of chemistry. But if I was better at it, geochemists can tell me exactly what mineral species will condense out of a gas as you cool it down over temperatures from 5,000 degrees all the way down to 30 degrees Kelvin. And that means that at each radius in this disk, you would expect certain materials to just drop out of the gases. Very refractory or dusty rocky species in here with a lot of iron, and silicates about here at a temperature of about 1400 Kelvin. Then there's the water ice line, and then different molecular species like carbon dioxide and carbon monoxide have different ice temperatures, different places where they become icy. And so at each radius in the disk, you expect different compositions, and it kind of matches what we see in these bodies in our own solar system, and we really want to know how this is going to map into formation theories for all those other bodies that we found around the thousands of other stars. Now the problem here, this sounds kind of easy. Oh, it's there. Well, it's at that radius. It should have this stuff in it. But remember those stories I told you before about the dynamics, how things move. So where I find things today is not where they started. And these bodies move all around the system in their early formation. And this is what makes it so complicated and so frustrating. Because I know that, and I'll show a slide in a minute, I know that Jupiter and Saturn and Uranus and Neptune in particular did not form from right where they are sitting. But location does matter, but it's not the only thing that matters in the story, like real estate, I guess. All right, so I wanted to kind of come towards the end with this very strange story of our system and tie it back to this issue of whether or not we are an oddball or whether we're the usual thing that happens. There again is a lovely fairy story about how Jupiter formed, and then it started to migrate in through these dissipative processes in the system. Saturn also formed and started migrating in, but because of its size and the way it interacts with the gas, it migrates faster. And it came in and then hit a resonance, a dynamical resonance between the Sun, Jupiter, and Saturn, and it caught it. It's like it threw a lasso, you know, whoop, boom, and it stopped Jupiter. Jupiter got into a certain distance, according to this fairy tale, probably close to where the asteroid belt is now. And then Saturn grabbed it, and then Saturn started to feel the pull of all the other stuff in the disk, and it started to pull it back ever so. And then they started migrating outward again. And this is called the grand tack, you know, as though they were sailors kind of sailing into the inner solar system. Oh, then they decided to go, well, we need to reverse, and we'll go tack back out again. Well, that's what's shown in the slide from top sort of to bottom. There's another part of the story where Uranus and Neptune are also migrating outward. And the story is super complicated. And the reason why we tolerate how complicated and weird it is because it helps explain some of the key features of our solar system. We have these big, nice terrestrial rocky planets here, but why is Mars so small? In all of our computer models, Mars should be bigger, Mars should be bigger, Mars should be bigger, but it's not. Well, maybe Jupiter came in and swept out the stuff that was supposed to go into Mars. Okay. Well, what about Uranus and Neptune? They moved out. What did they do? Well, they disrupted a huge fraction of this thing we call the Kuiper belt. These little bodies way out in the solar system. Our colleague David Gertis here in the physics department keeps finding new ones of these, even really big ones all the time. But this belt of little leftovers was much, much, much bigger. probably when the solar system formed. And we need an explanation for why it mostly, but not totally, got wiped out. And this big migration story helps to tell part of that story as well. It also, when it was doing that, it cast many of these bodies into the inner solar system. And many people believe that's how we got so blue and got so much water, is that a lot of this stuff from beyond the ice line got thrown in, and some of it went on to make our oceans. You may need some of that. You may not need as much of it as people think, but it's a super complicated story, but it has many, they're not predictions, right? They're explanations. They're explanations of many of the features of our solar system. And things like this probably happened in many systems too, but none of them happened exactly like in our system. So here we have a huge amount of complexity. We're trying to understand a huge amount of observational data, but what about the climate? You know, this sounds like weather to me. It's like I can't predict the weather on a given day, but over time I can make some more generalized statements about the climate. And the analogy I want to make here is, I don't know about the details of exactly how far Jupiter moved in and when Saturn caught it and stuff, but what I do know is, if the bigger planet formed first and started moving in, and then the second biggest planet formed second, but it's a little smaller, it will catch that first one. And that is a common thing that will happen every time when the big planet and the second biggest planet are in that same similar situation where the second one is lower mass. So that's like a common theme I want to look for in all those other systems. I doubt any system went through exactly our same thing, but I want to look for these dynamical themes in the system and try to see if I see broad categories that aren't exactly the same, but kind of have some similar elements. So that's our special story. You feel special? Everybody's special, right? But let's try to find the ways in which we're alike, too, right? That can be very, very important, particularly nowadays. I'm being very political today, aren't I? Goodness. All right, so what's the future? You know, it's never enough. We have a voracious appetite for discovery and finding new systems and new things. For me, the biggest, newest thing that will come soon is the James Webb Space Telescope, which we acronymize to JWST. There's a picture of it, a real picture, and those are real people standing next to it. It is a huge beast, which we're going to launch on a rocket. Now, we don't have a rocket that big, diameter, so we're going to fold it up first, like a child's toy. We're going to put it on a giant rocket. We're going to send it up into space into a place we can't easily get to. Then we're going to unfold it and put nice light shade around it, and it's going to work perfectly. It is going to work perfectly. It is going to work perfectly. I have to keep telling myself that. But if it does work perfectly, it is going to be an absolutely amazing device to understand star formation, how stars like the sun form, how planets form, and hopefully give us some insight into exoplanet composition through its amazing ability to take spectra in infrared wavelengths that we cannot observe here on Earth. It's going to be a truly revolutionary capability. But because of the problems I mentioned before about resolution, and in contrast, it turns out it's not going to be the very best instrument to take pictures of very faint things close to very bright things, partly because building an even bigger telescope in space is so unbelievably expensive. We would not ask our taxpayers right now to do that, a 30-meter telescope in diameter. We're just not going to have that in space. And because this resolution that we showed, that's what I need the most of. Most of the planets are close to the stars that I want to see. We need bigger apertures, bigger telescopes to get over that diffraction limit. And two of the big behemoths on the block are the giant Magellan telescope, shown right here, developed by the same consortium of colleagues that built the Magellan telescopes that Michigan is a part of. They are building a future facility which will be 25 meters across, very close to the Las Campanas site where the other telescopes that we use are. And I hope we will be able to be a part of this very, very exciting adventure in the future. That telescope is capable of imaging an Earth-like planet around the very nearest handful of stars. Now that's if some of my competitors were in the room, they would be objecting, but I firmly believe that that's true. I'll try to convince you at least, because here's a simulation of what the European version of this telescope, the EELT, can do around our very nearest neighbor, Alpha Centauri. Alpha Centauri is the best one to go for because it's so close by, but why would you not look there? So, if there is a planet at this distance, it would be pretty warm. It's not in the liquid water zone. It's closer than the Earth is, so it's sort of in this zone here. It's hot, but it's much easier for me to see in my thermal infrared goggles. So this is a simulation of what it would look like at 3 microns, at 5 microns. So the reddest thing your eye can see is about 0.7 microns, just for scale. So this is way out at the redder than the reddest thing you can see, but we're all glowing at these wavelengths. If you could take a spectrum of me or yourself right now, the peak of our emission spectrum would be at about 10 microns, because that's the temperature of our Earth that we're all standing on. And at that wavelength, this is a picture here. This is what an Earth-sized planet would look like around Alpha Centauri, out at the distance of the liquid water zone. So at 10 microns imaging with this telescope, we could, in principle, take images and spectra and find out what would be in the atmosphere. Now, I don't know that that planet is there, but if I build that telescope, that's the first thing I'm going to look at, to see if there's an Earth radius planet in the liquid water zone around the very nearest star to the sun. And you may have heard recently that there was a discovery of an Earth-like planet around the third star in that star system, Proxima Centauri, and that planet is very, very close to its very faint star. If you remember that plot I showed, can I go back to it instead of making you remember? Sure, I can. There. The Proxima Centauri is a star like this red one here, so its planet is down here at the edge of this habitable zone. That's too hard for me to image with taking a picture, but I could use a technique called interferometry that my colleague John Monnier is an absolute world expert at. And with 2 parts of that 25-meter telescope, I believe we could get a picture and a spectrum of that Earth-like planet around Proxima. But with Alpha Centauri, which is a star more like our sun, I could image that little blue guy right in the middle of that blue zone. Now, that's hard. Don't get me wrong. I mean, we need a decade or more of very sophisticated instrument development, and I'm starting a new laboratory effort here, which I hope will contribute to that here at the University of Michigan. But it's a goal worth pursuing, and I'll stand by that number. Maybe, I don't know, I don't buy fancy wine, but some people want $100 bottles of wine. I would bet that easily, that by 2030, there will definitely be a picture. Now, you won't see continents on it. It's going to be a dot, okay? There's not going to be, it's not going to be for you to upload on your mobile devices, but there will be a dot around a star with an Earth-like planet on it. I absolutely believe that. Well, we're not going to go there anytime soon, but NASA has started with its public relations department to make these, I think, very fun travel posters to some of our more exotic planets that we found through these various devices. And so it also gives you some evocative idea of what the environments are about some of these planets. So we're not going to get there anytime soon, but the future for understanding planet formation and the distribution of planets, I think, is very, very bright. And I think we will find many, many, many terrestrial planets. You have to catch me on my bet that I made here. We will have images and spectra of terrestrial planets. I don't even know if they'll be in the habitable zone, and frankly, I don't care. I just want to find little rocky things around the nearest stars and try to figure out what's in them and what they're about. And that will just take me a whole lot further, in my mind, than just focusing on whether they're in the liquid water zone or not. And I suspect when we ultimately get to the point where we might be able to detect biosignatures, they're not going to be of walking around people like you and me. It's going to be a hint of non-equilibrium chemistry in the atmosphere, and there'll be a little bit too much methane or something other weird, and we'll have to think about little bugs or little microbes that might help generate such signatures in the atmosphere. It's not going to be, beam me up, Scotty. We're not going to get there anytime soon. So let me end with this slide, which is a little bit tilting off, but I thought I would throw it in since this audience has been through this series this summer. Planet formation is super, super complicated, and I don't like that about it. As a scientist, as an empiricist, I want to find problems that are much more tractable, where I can make very clear hypotheses and test them and rule out the theories that I don't like, because I can never prove a theory. I can only rule out a theory that's wrong. And that's what my whole job is, I think, as a physicist. So planet formation is super complicated, and it's hard to make predictive theories I can rule out. But this idea of looking for climates or trends, I think, is an interesting one, and that's one we pursue in our research. But I was also struck by a couple of colleagues who were trying to make some grander statements about the relationship between complexity and processes in the universe. And I found this interesting. When you look at a system like ours that looks so special and so weird, but you also consider that the diversity and complexity of what we see is absolutely at the maximum. That's probably, in my opinion, the case that anything that possibly can happen will happen, like Democritus thought several thousand years ago. And our universe is so diverse and so complex, I think we fill phase space. And that means that there's a lot of interesting things to discover out there. And what this image is trying to illustrate is that there's a difference between increasing entropy, or the number of possible states that these specific glasses could be. And if you rearrange some of the coffee molecules here on the far right, you might not even notice it in the global color of the system. And you can try to define something like complexity, where this is a very low entropy or low number of states system with very low complexity. This one is an interesting one because it's medium in terms of its entropy, but it's very complicated because you're just starting to get the mixing going. And once you're fully mixed, you could argue that that is also an uncomplex system. And I wonder if our planetary systems might go in a direction like that. But let me leave you with the travel poster, which is a little bit more inspiring for the idea of traveling to other systems someday way beyond any of our lives. And thank you for your attention.